So in the last lecture, we talked about the ideal gas law and the individual gas laws and how they show the relationship between the different properties of gas. And in this lecture, we're going to talk about what other things we can calculate with the ideal gas law. And one of them is the density of a gas. And so the ideal gas equation, as we all know, is PV equals nRT. And we know that density is mass over volume. And so to find the density of the gas, somehow we have to convert PV equals nRT to include mass in it. And so what we're going to do is we're going to substitute N in the ideal gas equation with mass over molar mass. And so when we do that, we get PV equals mRT over the molar mass. So all I've done here is I've taken the N, which is moles, and replaced it with mass over molar mass, and we see that the density is equal to the pressure times the molar mass divided by RT. And so if you increase the pressure of your gas, you're going to increase its density. If you increase the temperature of your gas, you're going to decrease the density. So density is inversely related, density for a gas, I should say, is inversely related to the temperature, there we go, and is directly related to the pressure. So if you increase pressure, you're going to increase the density of your gas. If you increase temperature, you're going to decrease the density of your gas. And again, the way we get this is we take mass over molar mass and replace N with mass over molar mass. Now another thing we can do is we can calculate the molar mass of a gas by simply, once we replace N with mass over molar mass, we move the molar mass to one side and everything else to the other side. We get that the molar mass, we need to know the mass of the gas, the temperature, the pressure, and the volume. And so these are two additional types of calculations you can do with the ideal gas equation with some slight rearrangement of it. So we can calculate the density of a gas, and we can calculate the molar mass of a gas. So let's look at this example here. We have a compound sulfur hexafluoride, and we want to know the density at STP. So STP, what does that mean? It means standard temperature and pressure. So STP, we know that our pressure is 1 atmosphere, and we know our temperature is 273, 0.15 Kelvin, or you can just do 273 Kelvin. It's fine. And remember, for density of a gas is equal to the pressure times the molar mass divided by RT. So to calculate the density of a gas, and this puts it in grams per a liter, we need to know the pressure, which we do know. We need to know the temperature, which we do know, and we need to know the molar mass of the gas. And so we have sulfur hexafluoride, so that's going to be SF6, which is going to be 1 times 32 plus 6 times 19. And we get 146 grams per mole. So now we have the molar mass, we have the pressure in atmospheres, we have the temperature in Kelvin. We can calculate the density of the gas. So anytime you see STP, the temperature is always 273 Kelvin. The pressure is always 1 atmosphere. And we get a density of 6.51 grams per liter. So anytime you calculate the density of a gas, it's always going to be in the units, grams per liter. We'll look at another example. So here we want to calculate the density in grams per liter for sulfur dioxide gas at negative 15 degrees Celsius and 540 millimeters of mercury. So again, density is equal to the pressure times the molar mass divided by RT. Now here the pressure is given to us in millimeters of mercury. So we have to convert to atmospheres by dividing by 760. And again, when you do this operation, make sure you keep 4 or 5 significant figures, because if you round too much in this stage, it can cause a big error at the end. So now we have the pressure in atmospheres. We need the temperature in Kelvin. So we have negative 15 degrees Celsius. To convert it to Kelvin, we got to add 273. Now we have the temperature in the right unit. And lastly, we need the molar mass. So this is sulfur dioxide. So now we have the molar mass of the gas, we have the temperature and pressure in the right units, we can calculate the density. And again, don't be surprised that you think, oh, these densities are very great, but remember this is in grams per liter, whereas densities of solids and liquids are grams per milliliter. So these are actually quite small when you convert them to grams per milliliter. And we get a density of 2.15 grams per liter. So in this example, we want to determine the molar mass of Freon 11. If the sample of gas weighs 0.597 grams, occupies 100 centimeters cubed at 95 degrees Celsius and 1,000 millimeters of mercury. So here what we're looking for is the molar mass of this gas. And so what we have to remember is that the molar mass of a gas is equal to the mass times R times the temperature divided by PV. So again, the mass needs to be in grams, which it is. The volume needs to be in liters. Now 100 centimeters cubed is like saying 100 milliliters. So you need to convert this to liters by dividing by 1,000, because volume has to be in liters. Temperature has to be in Kelvin, so we got to add 273. And then lastly, pressure, as usual, needs to be in atmospheres. And the way we convert it to atmospheres is by dividing by 760. and we get 1.3158. So now that we have everything in the right units, we can plug it in and solve for the molar mass of a gas. Now you don't have to memorize the ideal gas constant. It'll be provided for you on an exam. You just have to need to know how to use the ideal gas constant in the equation. And again, this is going to be units of grams per mole. And we get a molar mass of 137.1 grams per mole. So again, to determine the molar mass of a gas, you need four things. You need the mass of the gas, the volume of the gas, the temperature, and the pressure. And typically when you do this type of experiment in the lab, the volume of the gas is usually the volume of the container you're using to contain the gas vapor. So if you're using, for example, a 100 milliliter Erlenmeyer flask, well, that's where the volume of the gas comes from. The temperature of the gas usually comes from putting this Erlenmeyer flask in a water bath, and the water bath is a particular temperature. So therefore, you just measure the temperature of the water, which is supposed to be the same temperature of the gas. And then the pressure, generally what you do is you poke a hole in the top of the flask. Usually it's covered with foil. You poke a hole in it so that the pressure is the same pressure as the atmosphere. And so from that, you can determine the mass of the gas and get the molar mass of a gas. Now we have one more type of, I guess you could call it an application of the molar mass of a gas. And that's going to help us determine the formula of a gaseous compound. So here we have a sample of sulfur vapor, has a mass of 0.767 grams at 294.1 torr, 405 milliliters, and 45 degrees Celsius. What's the molecular formula of the sulfur vapor? Now, before we begin to determine the molecular formula, we need to know the empirical formula. And the empirical formula of sulfur vapor is S. So this is the empirical formula of sulfur. And so its molar mass is 32 grams per mole. And so remember, to find the molecular formula, we need a value called N, which is the ratio between the molar mass of molecular formula divided by the molar mass of empirical formula. Well, the empirical formula we already have. It's given to us. We know sulfur, S. Its molar mass empirical formula is 32. We have to find the molar mass of the molecular formula, and that's where we're going to use the information about the gas to calculate the molar mass. So here, molar mass again equals mRT divided by PV. So again, the mass has to be in grams. Pressure needs to be in atmospheres. So remember, torr and millimeters of mercury are the same thing, except torr is technically supposed to be used at a temperature other than 0 degrees Celsius. So we're still going to divide by 760 to get atmospheres. And we get 0.38697 atmospheres. We have pressure in the right units. Volume needs to be in liters. We have it in milliliters. And temperature needs to be in Kelvin. So now we have everything in the correct units. We can find the molar mass of this gas. And again, this is going to be the molar mass of the molecular formula. And we get a molar mass of 127.8. So now to determine the molecular formula, we have to find N, which is the ratio between the molar mass of the molecular formula and the molar mass of the empirical formula. And we get 3.99, which is approximately 4. So the molecular formula would be S4. And so again, that's how we determine the molecular formula. We have to find the molar mass of the molecular formula. Generally, the information about the empirical formula will be given to you in the problem. And then once you know the empirical formula and its molar mass, you use the other information in the problem to calculate the molar mass of the molecular formula.